one specific case study, but then I looked at the other presentations that were there, where there's a lot of talk on OpenCV and all of that. And I thought maybe I'll present one of the problems that we face in agriculture, and that is the geospatial data, right? I mean, it's a massive problem, it takes a lot of memory, it clogs up your RAM, right? And how do you go about solving something like that? So there are, of course, a lot of solutions out there that can be used. But I just want to present one of them, which we have developed at IBM, and I welcome all of you to try it out. Even after the talk, if you guys want to get some insights or more understanding, please feel free to message me, and I'm happy to do the help you guys out anyway, right? So with that said, let me share my screen. I will spend some time kind of briefly going over the content, what is it, what is the problem, and so on. And then we'll do some, some demonstrations and exercises, and how the code looks like, and so on. So, you can actually apply it in your own real lives, and then your own problems. Right. So let me share my screen. Okay, let me know once you can see my screen. Okay. So let's just start with the problem statement, right? And I will not go through the entire slides, but I'll share with you with the organizing team for distributing to all of you. The biggest fundamental problem in agriculture the way we see it is, is there data available for us? Yes, there is lots of data available, right? So we should potentially be able to use this data for our doing of various things, right? But then most of the data that we need, whether it is satellite imagery or weather forecast or extreme event predictions, you name it, all of them tend to be very geospatial, right? They have two dimensions. They have a spatial dimension and they have a temporal dimension, right? So think about weather forecast. Now, if you want weather layers, or let's say precipitation layers, for even a relatively smaller area, let's say Karnataka, and you do it for the entire year, one layer per day, I mean, that's already going into terabytes, right? So that has always been the stumbling block in many ways. So if you look at all of the ag-tech companies, I'll give you an example of things like there's a company called OneSoil, which is really good at using geospatial data to do crop identification, all of that. When they had small data sets, it was okay. But when the data sets become big, even processing the data, basic, simple data pre-processing can be quite painful. And the next step is, of course, AI, right? So that's a big problem. And at IBM, what we thought was, we have to create a solution that solves two problems, right? One is we should make it easy for people to get the data, right? For example, if you think about weather data, and if I ask all of you, what is your source of weather data? I mean, we will come up with at least 10, 15 answers. We could potentially come with 10, 15 answers. Now, for example, we can think of ECMWF. We can think of, NOAA data sets. We can think of, IBM weather companies data sets. We can think of, so many other things. And all of them have their own things, right? So, for example, ECMWF has certain resolution, certain temporal resolution, certain spatial resolution. If you go to some other data set, it has a different resolution and so on and so forth, right? So what is the right data set for you? It can only be decided if you get access to all of them, take a look at them in one glance and understand what makes sense for you, right? So one of the key things that we had to do is we wanted to see if we can curate our database such that you can go to this one place and take a look at all of the data sets that are available for you, and then pick the right one that makes sense, right? So in the IBM Physical Analytics Integrated Repository, we have around 5 petabytes of curated data sets, and this is a list that is continuously growing. And what we have essentially done is, enabled faster execution. You can do a lot of things at the server itself rather than downloading it. So that kind of reduce the cost, right? And everything is nicely categorized. We'll go through all of that, when you see, right? So that's the thing. So the proposition is simple, right? So we already aligned everything. All the layers are there. all you have to do is, query them like you would query in Python, and then, download the data sets or process them at the server and only get the insights that you are requesting for. So I will again go through all those examples. So what essentially it turns out is, if you take a look at what people generally do, if you have a do-it-yourself geospatial mindset, you are going to, probably spending this kind of time, right? I mean, transforming the data, indexing it, ensuring that the transformations are right. Everything has the same projection. And also look for errors. So all of these things, the pre-processing part of it takes a long amount of time, and then you have the remaining amount of time to actually actually work, do what you want to do. With pairs, it's very simple. Now we have curated everything, as I mentioned. So you have all this time that you can use for doing data science related work, and understanding and then taking it 2 steps forward. So one of the aspects is all the layers are aligned. So it doesn't matter what resolution, they're all aligned vertically, temporally they are aligned, right? And the way it is done in pairs is we store this data not as like a shape file or a TIFF file, like raster file or vector file. We use a fileless system, right? So it is very easy and very fast to query the data. So if you want, let's say for a given point, yeah. So let's take a simple example, and by the way, feel free to stop me in the middle and ask a question. That's completely fine, right? And I think it's like a lot better way of learning, also interactive, right? So one of the things that we do here is we query all of these data layers are there in what we call as a fileless system, and the idea there is quite simple, and that is we don't store the data as a raster file or a vector file, right? Everything is stored as in a key pair system. So in a typical scenario, let us say you want temperature data for a given location for the entire year. Well, the way we do it generally is, you have to read each file, pick up that value, and then, do that for all the layers, and then get the thing, right? And that can be quite painful, right? So because if you have a large map, then this might not be the easiest thing to do, right? On the other hand, in here in pairs, the way the data is set up is we hold them in key. All the temporal dimensions for each point for a given file are held in one record, right? And it is a fileless key pair record. So when you access the data, you can read the temporal dimension, very fast, as well as the spatial dimension also, right? So that's an interesting aspect that we can do here, right? So there are many use cases that we have put forth for this, from insurance to agriculture to energy and utility to consumers. So there's a lot of use cases that are coming up, and we are essentially using the data for the same. So a lot of examples also, and we'll go through some of them. So you can see from climate change to customizing weather forecast, applying deep learning algorithms, doing energy trading, even COVID-19, wildfire analysis, vegetation management, greenhouse gas emission. So all of these things, there are already examples that you can actually use to get started with this whole thing, right? So the access is quite simple. You can go to this. I'll talk about the location later. We have a website, dedicated website. You can go there, or you can give me your IDs at the end of the call. Maybe it can be collated and given to me, and I can get the demo accounts for you guys to kind of explore. So there are 2 ways you can actually access the data. One is like in a GUI kind of a thing, right, where you can visually go and see how to pull the data. Another one is you can query from a Python program. And we'll again do both some examples to understand how we can do the same. So it's just an example of a visual thing, right? And but you can also do the queries. So we have APIs And one of the very powerful things is what we call as a user-defined function, wherein what you can do here is, so let us say you have the data layers, and in a typical workflow, you might have to download the data. So let's say I want to calculate the spatial average of precipitation at each district level, right? Now, in this case, you have to download the data from Python, from whatever source, typically speaking, and then you have to take your point shapefile, the shapefile, apply that, then calculate the average, and then come up with the statistics, right? Now, the problem with that is the downloading part, and the downloading can be quite painful, right? I mean, you download the data, it's going to take some time, then you got to compute it, and all of this is going for a simple exercise, right? The exercise was very simple. We just wanted to calculate the spatial averages, and yet it's going to take a lot of time to do the same, right? So one of the things that you can do in IBM pairs, which is very unique to our solution, is you can do all these simple calculations, right? And your own calculations, whether it is spatial averages, temporal averages, right? You can apply your own functions, and you can do it in the server. So you don't have to download it, right? So if you want the average in the case of pairs, you just have to write a particular query in a certain way, and push that query to the IBM pairs. In the IBM pairs, the calculations are done. It is computed there, so it is much, much faster, right? And then the data that you need is pushed in as an output. So you can download them as CSV file, or download them as a data frame in Python, however, whatever is convenient to you, right? And this is a major advantage when you're dealing with geospatial data, because a lot of the times the goal, at the end goal of a geospatial data, is not to take the entire data as it is, but rather calculate the spatial averages or the temporal averages or some other kind of estimation, and then use that same thing for your own purpose, right? And this is a very powerful feature that you should that you'll find very useful, especially in the agriculture sector. So this is what I was talking about, right? So we'll go through this example later. So you can do raster queries, you can do point queries, you can do polygon queries of various data sets, right? Over 429 data layers in 50 data sets are available. So whether it is satellite data, aerial imagery, elevation data, soil data, everything is updated the moment the data comes in. Is released. They are automatically stacked. And another interesting feature is, there are new satellite data sets coming up, 10 meter, 5 meter resolutions. I know those are also being made available. So in many ways, if you're trying to do exploratory work, or if you're trying to create a solution, you can definitely explore what is there in IBM pairs, because it cuts out a lot of this initial steps that otherwise you have to do on your own, right? So so that is that. So this is some more examples that we have. So this is where you can actually can download the data set. So I'll just take 1 second for you all to take a screenshot of this, right? I'll just count 5. You can take a screenshot and keep these things ready. So when you are done with it, you can go there and access the various things. So if we just count 5, 5, 4, 3, 2, 1. So I'm hoping all of you got this, right? Can you move ahead, Ganesh?
Yeah, you can. I'll share that screen in the chat also.
Yes. Okay. Yeah. Okay. Thanks. So there are a lot of tutorials ready to go, and after the session, you can do it yourself also. Again, feel free to message me. My email is there, so please feel free to ping me, and I'm happy to support in any way that you can. I can, right? So that's that. So let me just quickly go through, and I just want to go through this particular slide on the pair side. Why is this interesting to us? So this is a graph that talks about the query data size and the query time, right? So if you take up any of the current existing ones, including the open data sets available on Amazon and all that, right? They generally tend to follow the curve at the bottom, right? So the bigger the data size, you see the query time, increases quite a lot, right? So what we have done here is, we ensured that the scalability is achieved, and so we are kind of right in the middle in terms of the query time versus query data size. So for most of the data sizes, you are able to achieve the maximum performance, for your purposes, right? So that is that. So that is pairs. But then let me talk about some agriculture specific solutions that are already there in pairs or as built on the pairs platform. So we call this as the Watson decision platform for agribusiness. And there are multiple components which are available in pairs, but some are also available separately. And one of them is HDNDVI, which is essentially NDVI data, but then all of the pre-processing steps like cloud correction, right? Filling up, let's say, when you have lots of clouds, how do you still get a map, right? So all of those things are done in this HDNDVS. So to do this, we actually fuse Sentinel-1 data, which is independent of clouds, and Sentinel-2 data to make it happen. So that data is available on the pairs platform. There is something called as a HD soil moisture, which is a very unique product because you can get soil moisture data at the surface as well as the root zone, right? So you can define what is a root zone, and here the way we do it is, we blend optical, thermal, and microwave data, and there is a little bit of physical models also involved. So there is a set of physical models called as land surface models. We use the land surface models to kind of to provide this HD soil moisture. Now, what is available is 1 kilometer by 1 kilometer, but there is a 250 meter by 250 meter also available that can be also readily consumed, right? Now, this is just the products that IBM developed on top of what is, other public sources. So things like SMAP, right? All of these data sets are anyway available. These are just additional things that we can add. So there's one called Plant Pathologist, which is very specific to some crops. So we have weather-based disease risk scoring. So we have them for some of the crops. Then we can always, other crops if we know the relationship between the weather and the diseases, right? So that's another element. There are ready-made algorithms that you can use for crop identification, acreage estimation, and so on and so forth, and yield mapping and fruit count. So there are multiple tools that have been developed on top of the pairs, and that can be used independently. So where do we see the value for it? We see from planning all the way to post harvest. We have done many use cases with clients where this data has been used. So I think let me just quickly go on the technical side of it, right? So why does this HD NDVI sound is an interesting one, right? So if you think about the current NDVI data, right? You have the MODIS, you have the Landsat, and you have the Sentinel data, right? Now, all of them have their own time resolution, right? So MODIS is daily, Landsat is 16 days, Sentinel is 10 days. Now, on the other hand, MODIS is 250 meters, Landsat is 30, Sentinel-2 is 10 to 20 meters. Right? So what we essentially do is we combine all these three for you, right? If you were to do it on your own, then you have to download each of them and then come up with a solution, right? So what we do is we do this fusion activity within in the server itself, so you don't have to do it, and then we come up with our map. So if you take an example here, this is the MODIS, this is the Landsat, this is Sentinel, and we can essentially come up with a map that you can use for your purposes. So a quick example of cloud correction. So if this is the HDNDVI and Sentinel data, you can see that this is quite different, right? And why is it important for agriculture? So if you think about agriculture, most of the growing season, right, you tend to have this cloud cover, especially in critical parts. You tend to have cloud cover, right? with the cloud cover, it can be, all the work that we do can be actually not as effective. It will still be as effective, right? You have we can do our various solutions without having to worry about the cloud coverage, right? So that was the motivation for this particular in the years, right? So now this is another example when sometimes when you have the Sentinel satellite going, you have some tiles missing, right? So we can actually even close that gap and ensure that the data is complete in many ways. So that's another additional value for SD and DVI. Now we can detect crop stress, and we have done this. I think everybody has done this before. So we can. There's also options to do go into sub-acreage visibility, right? So we can correct the NDVIs, and all of these algorithms are also built into the system, right? Another one is automated boundary detection, and I think this is very important for plantation management, right? And one can always detect the boundary for the entire plantation, but what if you want to detect certain specific zones, of the plantation? So that kind of automation can also be done here. And we have to kind of demonstrate the same across the area. So I think these puns we can move. I think again this is an example of the boundary detection. So I think yeah, Sentinel. Yeah, I think this is all more technical. We can probably go to the. Yeah. So I think what I'll do is I think I'll just see what are probably relevant, right? So we have some yield models that are already built in, and you can access the same. So there is one, for example, palm oil, right? And we have this. So if you have database specific to a given crop, we can even update those things and ensure that you can use the same for mangoes or so on and so forth. So that's another element that is there and that can be customized also, right? There is also some solutions on the pest and disease prediction. So here we use we basically the way we did it was we scoured through the literature, saw what crops and what things have their own crop models, disease and pest disease models, and then we basically implemented the same for ease of access, right? So that's another thing that we use the pairs data for, but something that you can also do for your own crops, right? So I think what I'll do now is I think that hopefully provided some overview. So what I'll do is I will go now to the more interesting part, the demo part. Presentations are good, but it's always better to do the demo side, right? So this is the environmental intelligence suite, or pairs as we call it. Both are the same. So this is where you can actually you can get access to various things. And what I'll do now is I'll go through some of the various ways you can access this data, and also show some code on how we can code the same for for various things, right? So this is the website, and let's just start with the dashboard, right? And this is the environmental intelligence suite, or the previous name was pairs. And once you get your access, you'll see these three things. One is called as dashboard visualization, and geospatial analytics, and alert console. So you can actually add your own tools for that. So let's just start with the interactive map, right? So if I so this is like a visual tool, right? So you can add your own layers and see how various things are doing. So as you can see here, I can pick various radar things. I can do precipitation accumulation, pressure contours. I can do soil moisture. So let's just pick maybe soil moisture, right? And if I close this, so there you go. So you can see that we have the soil moisture data that is coming up. Now you can do this for various dates, right? You can go back and visualize, and get a sense of what is happening. So now this is 1 kilometer by 1 kilometer, right? And you can take a look at other things, like for example, soil temperature, water temperature, road weather. You can even take a look at road weather, things like that. You can add other aspects. For example, you can add, is there any flood event or any earthquakes, right? Traffic incidents. So all of these things, now compare this to some other solutions that are out there, like QGIS, or you have to do this kind of manually. You have to first of all know where is the data, then you got to download it or do it online, but still there is a little bit of steps involved. But here, essentially, all of it is curated. So one thing we do in pairs is almost every data that is available today in public, and definitely in public and some in private, all the data that is there, you can find them here. And therefore, it makes your life a lot easy to kind of play around, right? So you can do various asset data, you can customize, you can add boundaries. So, this is only for basic visualization. Now, there is another layer called Vegetation Management. So let me just can go here. So, right. So this is specific to forest areas and things like that, right? So it's not probably very relevant to us, but this is there. And this is currently being added and developed. You can see various issues that are there in the vegetation part, right? So that's so there's like visualizations you can do on this part. The more interesting one that you might find interesting is the geospatial analytics, right? So let's just click that and let's take a few examples. Let's run through what are already there, and then we'll create our own example to see, so as an example, let's take a look at this drought monitoring. So this has already been, somebody has queried it. So, this is already there. So let's take a look at it. So if you think about the map, right, this is almost the entire Horn of Africa kind of area, right? So this is quite a significant area for computation to be done. But yeah, so let's see. Probably my internet is not that fast. Just 1 second. Yeah. Just waiting, guys. 1 second. My internet's slow too. It's a little slow here. Maybe we'll do our own query. Yeah? So let's just see how that goes. Okay. So let's just start with a query. So we'll just create query. Yeah, I think while that is loading, let me show the examples. I think I already have it ready here. So you can see here that you can query various things. Like this one is talking about population density of Europe. This is the onset of winter in a particular state. This agriculture farms in Maine. This is drought monitoring. So you can actually draw a square and do the same for any place in India. Elevation, crop, soil data, precipitation data, these kind of things you can download here. So this is another example of that. So we also have like Landsat data, right? So let's just see if we can pick one example. Let's just click maybe Landsat. Some reason, just when you want to demo, things go kind of weird. So it's not cooperating for some reason. So. Okay. For some reason, it's not cooperating. So, but basically, you can query various things that you're interested in, and yeah, I think yeah, this is kind of not working when I have to show. So so maybe we'll just check back on this. There seems to be a server error. Okay, so we'll check back on this later. But let me show you how to access the same data through an API-based query. Okay, so so this is the website for the various tutorials, right? So let me share that link in the chat. Okay, so that's the link where you can actually get started on various how we can do it. The solution essentially requires in Python, if you're using Conda or pip, you can install these things with the package called IBM_pairs. And once you have the IBM_pairs, you are ready to go, right? In the backend, essentially IBM pairs, has the server linkages, authentication protocols, as well as geospatial related things like JDAL and everything already installed in. So you don't have to separately do it. So you can also install it with pip if you want. Pip install IBM pairs and do the same, right? So once you install the whole thing, you can get started on the queries, right? So let me quickly go through how this is essentially happening. Okay, so so the way you do it is, let me just zoom in for clarity. So you get outputs as a JSON. So you import the JSON file and you say from IBM pairs import PAW. PAW is the pairs authentication workflow, and then the authentication. So you just import these two things, right? So when you get an account in pairs, you will get an API key. So you put in that API key here, and this is the server which will be providing you the data, and the credentials essentially you can put it this way, right? And once you have this, then the query starts, right? The query now, you have to create a JSON kind of a thing to make the query happen, right? So the query JSON essentially has multiple things. The first thing is it will ask for what are the layers that you're interested to query, okay? All of this data that you see here, I wish this opens up so that I can show you. All of these layers, essentially, they have a so they have an ID, right? So what you essentially do is, you can go into the pairs visualization, check out all the layers that you're interested in, and whatever layers you're interested in, you basically pick up two things from there. One is, what is the type of it, right? Is it a raster file? Is it a vector file? And what is it that you're interested in? So that's the first thing you ask for. And the second thing you look for is, what is its ID, right? And each of the layers has its own ID. Now, let's take the case of weather precipitation data, right? Now, there is a source called Prism. Okay, so if you download the Prism data, all of the Prism data will be, whether it is for today or tomorrow or day after, all the temporal aspects will be stacked in the same ID name. Okay, so a ID refers to a particular data set, right? And 16100 might be some particular data set. Now, once you have that ID, then you can query in two ways. You can either query at a point, you can query spatially. So you can go point, you can go polygon, you can average over an area, you can do those kind of things. And you can query over a certain time period, right? So if it is a weather data, naturally there will be a starting time and an ending time, right? Or you can give a snapshot. So for example, you can say, I want weather at 4:30 on the 26th of July, in which case it is going to give you the weather for that particular time, but then it will see in the data what is the closest time data set that is there to what you have queried. So if you have queried at 4:30 and the data sets that are there are at 4 and 6 o'clock, it will give you the 4 o'clock data set as the output, right? So you can see that first you give the layer type. Now you can give multiple layers. So you can do multiple queries at the same time, right? You don't have to write one query for every layer. You can do multiple layers and then you can finish that entire task in one quick shot, right? And once you give the layer type, the next one is you give spatial. So how is it that you want the entire thing to query, right? Do you want a point data? Do you want a polygon? So what is the exact spatial query you want to happen, right? So the spatial query in this case is point. So I'm saying spatial type point. Coordinates is I'm giving the coordinates, right? Now you can give multiple coordinates, you can give multiple points, and that is up to you, right? Similarly, you can give a polygon data if you want. So that is the spatial part. The temporal is you have again options. You can give intervals, right? Or you can give snapshots. You can say, I'm only interested in a certain specific time, all right? And then essentially to look for that particular aspect, okay? So if I take a look at the 1600, so this is what you create the query. Once I create the query, then you basically submit it to the pairs server. And what the server will do is essentially give you a job ID as an output, right? And then essentially you wait for the job to be finished. Once the job is finished, the file can be downloaded, to where, to any other format that you're interested in. So in this case, we said I want 16100 data set, which is the temperature forecast data. And I said, I want between 2015 January to 2018 December. That's quite a significant amount of data, right? And if I give that, this comes down to around 10,000 records, right? So in this case, you just get the entire data set as simple CSV file. Now, 10,000 records of data, if you were to do it on your own, right, you would have to download all of these files and then do the calculation, and it's going to take some time for you. But here, because the entire thing is done in the server, when you say query is equal to pod.pairs query and you give the query JSON, the query variable here is actually going to hold that data frame, okay? Because it is fast. 10,000 records is fast for pairs, so it can do it very quickly. So once you submit it, you will get that entire file, right? And you see here there are 10,000 such records. You can see here that's a data set, that's a layer ID. So if you give multiple layers, so let's say I said type raster ID 16100, which is for temperature, and I give something else, type raster ID 61, I don't know, 200, which could be, let's say, precipitation. Then all of the data will be returned as only one data frame, and that's a beautiful thing, right? So you can see here, it will layer ID, there can name, the latitude and longitude. So here we are given only 1 point, but if I given multiple points, it will essentially return multiple values, and it will give the timestamp. So this is a standard Unix timestamp. That's the value, right? And that is the time, right? So, and then the point. So all of the data essentially is written as a data frame. Once it is in the data frame, then you can do the rest of the Python activities to take it forward, right? So this is the time interval that we gave for. So we got the same. So that is essentially one way to do it. Now let's take a look at some other examples. Yeah. So let's take a look at this example here. So in this example, I have given the raster ID 91, which could be a certain data set. I've given a temporal date, so I've given time, and then I said aggregate it, calculate the mean value, right? So it's going to take that thing and estimate the mean value for me. Similarly, here I have given maximum value and and then got the same data. So if I do the same, you will essentially end up with multiple values of the mean value of the various things, the maximum values, and get the same data, right? So this particular tutorial folder is something that is very easy to follow. You can get started with the raster data. So this is a simple example I gave you, right? You can do the same for vector data, right? Get the same thing. You can take a look at spatial coverage, right? So here, we are looking at point, but you can do the same thing for square. You can do a polygon. You can provide all of those things, right? So you can provide different spatial coverages. So there are some polygons already in the platform. So for example, let's say you want to get the average NDVI for the state of Karnataka or some district, right? You don't have to, get that administrative file and then do all of that. It's already there. So you just have to say what is the ID of the polygon, and you just put that ID name and then ID number, and then you essentially get the work done already, right? So as you can see, a lot of things are essentially preset, so that you don't have to worry about it, right? And if you want to know, what is the polygon what is the ID of the polygon I want, you can also get it through programmatically. That's also a quick example is here given here. So you can see here, I can query saying that, hey, what is the polygon ID for the country Japan, right? And if I do that, essentially you'll end up with a response and you'll get the same, and then you can use the ID to make the various calculations. So that's on the spatial side. You can aggregate them, as I said, right? You can do spatial aggregation. So for an entire region, you can say what is the average NDVI or average soil moisture. You can do that kind of calculation. Quick example here. I can say here, you see here, this one is, I'm saying for the certain data set of ID 92, I want to get the maximum value for the raster. And then the spatial is essentially the polygon here. Now this you can give yourself, or you can use the preset polygons, right? And if you do that maximum value, you'll essentially calculate the maximum value for the spatial data across all the time, right? So for each timestamp, it will calculate the average value and then give you the output. So that's another way to do the same thing. So you can see here, I can do the same. So there is an aspect called dimension. This is basically time, right? So if you're interested in multiple times, you can add multiple times and get the same thing. So that's essentially how you can query from pairs. So we'll just take a look at a few examples when we come to that. So you can get started with this exercise. It's very straightforward. You just install your IBM pairs and get your authentication from the given websites. Once you have it, if you run a few examples, you will get a very good idea of what is essentially happening. There is also more examples here. So on cloud-free satellite images, bias correction for weather forecast. So you can do all of these examples also in the tutorials here. Now, at this point, I want to kind of point out to one interesting functionality in IBM pairs, which is called as user-defined functions, right? What is user-defined functions? User-defined functions are essentially complex mathematical calculations you can do at the server side. So you don't have to download the data and do it yourself, but rather you can perform that same calculation there on the server and only download the outputs. Now, I cannot underestimate how valuable this tool is, right? And especially in agriculture. Let's say you are trying to calculate, let's say for each grid of your farm, what is the average NDV or the maximum NDV? You can do all of these calculations upfront, in the server side, and then download the values for your purpose, right? So what does the user-defined function do? So an user-defined function essentially is you can write a complex calculation. I'm just trying to find a good example. Or maybe we have better examples. Let's see. Okay, so if you see here, yeah. Was that a question for me? Okay.
I think no, sir. No, sir.
Okay.
Can we access this data free? Okay, maybe a little. I think chat box, sir. Someone raised a question.
Okay. Will this PPT be shared? Yes, of course, we'll share everything once this is. Can we access data for free? Yes. The basic access is free, right? So you can definitely explore it, right? And I think there is also some kind of relationship that academic institutes can use, right, with IBM pairs. So if you guys access it, see if you like it, and if you want to have further questions, please feel free to contact me. Yeah, Abhishek, Dr. Abhishek. Great. So please, feel free, and I'll connect, get these things working for you. Okay. So let's take a quick example of what is this user-defined functions, right? So let's take one example where I want to calculate the average data, right, for a particular raster. It could be like a precipitation data, whatever. But for the sake of it doesn't make any sense in terms of utility, but it's a good way to show that example, right? So let us say we have a layer, and let's call that layer ID 48869. Okay, we have this layer. Now, in this layer, I want to take the average value for the maximum for each of the 3 years. Okay, so I want to calculate the maximum value of this raster for the years 1981, 1982, and 1983, and then I want to calculate the average on top of it. Okay. Now, if you were to do this independently, it's going to be quite painful, right? So you have to download the data, and then you got to essentially apply your various algorithms. Once you download the data, this is a very fast activity, right? It's quite simple, right? So you calculate the average value, the maximum value for each of the years, and then you calculate the average maximum value for the 3 years. This is the problem statement. Now, the way you can do it is, of course, as usual, is you can download and do that. Another way to do it is you can actually query 3 layers, right? So take a look at the first one. In the first query, I'm saying, hey, give me all of the data for the year 1981 from, for this particular thing. So sorry, this is 0102 to 01. Yeah. Start is 0101. So it's only for 1 day. Okay. So on the 1st January, I want to know what is the average maximum value for the 3 years. So you see the first one, the temporal starts in 1981-0101 and ends in 1981-0102. Okay. So it's only for that first day of the year, for the year 1981. I'm getting the maximum value. Okay. And then what I do is I create an alias for it. I say this particular query, right? Please call it as data 1981-0101. Okay. So that's the first one. The second one is the similar thing, but for the year 1982, the 1st of January. I'm calculating the maximum value and I'm giving it an alias name. I'm calling this as data 1982-0101. And similarly, I can do query 3, 1983, same data ID. I'm going to also calculate the maximum value. And then say data 1983-0101. So I have done basically 3 geospatial queries. Okay. Once I have done these 3 geospatial queries, I want to actually calculate the result on the server itself. I don't want to get it here, right? So I'm going to say, now do a computation and call it as, give it a name, result 0101. And the way to get this result 0101 is I want to take these 3 aliases, the data 1981-0101, data 1982-0101, and data 1983-0101. So I just take these 3. The $ means that it's an alias name. Okay. And then I say, add up all of them and do divide by 3. And I can do the calculation. And then the spatial coordinate is essentially, this square. So I'm going to calculate about this entire square. Yeah. So the problem statement is simple. You have a region, you have a square region, you want to calculate the maximum value of that parameter on the 1st January for all the 3 years, and then want to calculate an average. So that's what we have done here. The first 3 queries will essentially query the maximum value polygon, right? That square, maximum value for each of them. And you'll put it there. And then once you have that, you essentially do then the average, right? And then you get the output, right? So again, the temporal, here this doesn't matter, so don't worry about that because the temporal is already here. So once you do that, you have you get the entire output. Once you created the analysis, right? You calculate, and you essentially end up with the expression value. Okay, you'll get out the entire output, and then that is the one you can use. So this kind of writing expressions, right, that uses the previous queries, no matter what it is, okay, is a very powerful tool that you can have. Now, can anybody tell me one example in agriculture that you feel you can actually put this user-defined function to? Anyone? Any thoughts?
Some short messages are there, sir.
Oh, chat messages. Okay. Yes, disease forecasting is a great tool, right? I mean, I got one question here, sir. I'm a plant pathologist. Just call me Naveen, yeah? I don't feel very sir-like, so I'm just Naveen. So yeah, I'm a plant pathologist. My question is do I need to be an expert from ID to design? I think if you can see Dr. Abhishek, this is something you can do, right? It's quite straightforward. I think what you have to pick up is the skill in Python, right? And once you have a Python skill, then these kind of things can be built very easily on your own, right? So I would say the first step, right, towards becoming an expert is actually starting the thing. And this is one of the things I have found in agriculture is that there is a little bit of, especially agronomists, and there is a little bit of hesitation to do the coding, right? But let me assure you that it is the easiest thing. The most difficult thing is actually to understand how plants grow. That is for me the most difficult thing. The easiest thing is to code, right? And it only is, coding is a creature of habit, right? In my opinion. So we just have to start somewhere, right? And I think once you start and try to do this kind of examples, right? And, then it becomes a lot more easier, right? It's 1 week of work, but then once you get a handle of it, then you are not looking back, in my opinion. Yeah? So does that answer your question, Dr. Abhishek? Great. So, so some of the use cases. So people were saying, you can use it for disease forecasting, right? How can you use this for disease forecasting? This kind of user-defined functions. Well, let me ask you a better question is, why do you think we can use this for disease forecasting, right? And the simple answer is, if we all think about disease forecasting models, right? What are those models look like? Do those models look like some complicated physical, simulation, or do they look like simple mathematical expressions? Anybody? They are very simple, right? I mean, think about Jolsa cast or any of the potato early blight, late blight models. They're all very simple. They take a look at temperature for a day or for 6 days or 7 days, whatever it is. And then they see, is there a particular trend? They look for a certain trend, right? And if the trend matches, then they say that, yes, a disease is going to happen today in this particular farm, right? They look at RH. Relative humidity is a good example of use that is used. You sometimes use precipitation. You sometimes use dew point. You sometimes use temperature. All of these used in conjunction with a simple equation, right? And I think there is a 1 or 2 very interesting documents that are very specific to India, right? Where rice models are developed for pests and potatoes and so on and so forth. We have this model. So think of this thing. You can actually generate a very fast model, right? It's basically you take this code and apply the same logic, and then you are done, right? And so that is where I think this becomes very interesting in agriculture work. Another interesting example, I think Mr. JP Sharma has mentioned, is the rainfall forecasting. Yes, you can get an average rainfall forecasting data from this. You can use simple expressions. As an example, you can say, let us say you are interested to know flooding due to excess rain. Yeah, flooding due to excess rain. Now, flooding due to excess rain can be easily written with an expression because we know that for a given soil type. So first thing I can do is I can make a query of the soil, right? And if I know it is a sandy soil or a silty soil or a clayey soil, I can build a simple model, right, with an expression that says that if the rain from one of the layers I queried is more than 2 centimeters or half a centimeter, I can say that is going to be a flooding event, right? And I can do the same for the entire region in very simple query, right? Do you guys agree with me on that? So I can do extreme event forecasting as an example, right? Another example that you can think of, and it's a very important example, by the way, is GDD, right? Growing degree days, right? So what goes into a growing degree day calculation? There is a minimum temperature, there is a maximum temperature, and then you take the daily temperature, and then you basically keep on cumulatively adding these things, right? And then once you have the GDD for a given crop, now think of plantations, right? I mean, if you know the GDD from the start of the season, you can essentially say when it's probably going to flower, when it's going to fruit. You can come up with this kind of things. And using the GDD, you can actually calculate what could be the potential yield for a given region, right? So you can kind of look forward and say, until now, the weather was like this, the GDD is so much. If everything from here goes perfectly, this is the maximum yield I can expect, right? So you can do crop yield estimation with simple algorithms like this, right? And so on and so forth. So if you guys have any specific such queries, and if you have a specific problem, please find me on LinkedIn. I'm on LinkedIn. I'm on on email, and I'll be more than happy to show how you can use these kind of things to make some predictions, right? So that's the use of UDFs, okay? And let's now just go back and see if this server is working. Okay, let's see. Soil fertility, Rajashri, Shekde says you can use the UDF functions for soil fertility. And that's a very valid point, right? I mean, you can again build expressions saying that if the nitrogen is so, the phosphorus is so, you don't use, you say low fertility or high fertility, so on and so forth. Yes. So thank you, Rajashri, for that example. Right. So this is what I was talking about. So you can actually build your own queries. So here, this is NDVI data for the entire place. And, this is, you can see here, I have all the temporal queries also. You can pick any particular point and essentially it will generate the curves for you. Now, this is very difficult, by the way. Now, if you try to do this in other platforms, it's going to be quite painful. You always get the spatial side. You generally have difficulty doing the temporal part. Okay. It's very difficult to do the NDVI data across time very easily, right? And that is the strength of this, right? So you can actually see how fast I can move from point to point without having to stretch too much, right? So this is MODIS data. So if I go back to India, right, I can pick any location and I can do the same thing, right? So you can see here, I can pick the location and you can see, let's go to the river side. So you can see it's a lot more stronger, right? Let's go to a drier area. You can see, you get much lower areas, right? So you can essentially, query various things. So let's build our own query. Why not? I would say. So let's try to build our own query. Let's start with, hopefully it will cooperate. Okay. Okay. So let us see. I'm just going to say create a query. And I'm going to say add layers. The first thing we need to do is add a layer, right? So let's just select, let's just think of something. Let's say soil moisture. Okay. So there are lots of soil moisture. As you can see, the moment I hit soil moisture, a lot of examples that have come up, right? So this is entirely all of the soil moisture data sets that are available today, right? So you don't have to be, affected by the fact that you didn't know that something existed, right? It's all here. So you can see your volumetric data set from 0 to 10 centimeters, 40 to 100 centimeters. So if you're thinking about plantations, thinking about things like that, you can pick the right thing of your interest, right? So let's just pick one example. So you can see even things like soil organic carbon. Yeah, you can see nitrogen. So let's just pick nitrogen. Okay, I'll say nitrogen. Let's call this. Yeah. You see here the tick mark is done. So I'm just going to say next. Okay, and then I'm going to say what do you want, right? So do you want the mean value? Do you want the 50 percentile, which is the median, the 5 percentile, or the 95 percentile? So just pick mean. And then you can also pick the depth. You can say, I want 0 to 5 centimeters, 100 to 200, or what? Right? So I'll just say 100 to 200 centimeters. Let's say 0 to 5. Right? There are, of course, more depths that you can pick. Right? If you do it in code, you can actually aggregate them across depths. Right? So you can say next. Right? You can then pick an area. So let's just pick a smaller area because there are 250 meter grids. Okay, I'm just going to pick this area. So you can pick a point, or you can pick a rectangle, or you can pick predefined areas that are already there. So I just picked this one. So you can see here, it says it's only a 2 MB, less than 0.002 to 0.002 MB. So it's not at all very big, right? So I can maybe try a maybe a bigger one. Let's see the size. This is 0.02, maybe slightly bigger. Why not? Right. So you see this kind of quick calculation, that's 1.418 MB. So okay, that's reasonable. So you can say, and here the time doesn't matter because it's it's from soil grids. So it's the same data. So we'll just say next. And it says, do you want any temporal aggregation? I'll say no. And just for the sake of it, let's make it mean, because as you can see, it doesn't change. Now I can call this whatever I want. I can say nitrogen near Aurangabad. Yeah. So Dr. Abhishek, to answer your question, this is something you can do even without coding, right? So you can actually get in and code and see how you can extract this data, right? So I can say, and then you can say run, right? And once I say that, it is going to query it for me. So you can see here that it is waiting. So you can see it's 5%. So let's just. Sometimes it tends to be a little slow, but generally it's okay. I think today's a kind of an off time. So essentially, once you query, you'll get the map. For the sake of time, let me just quickly jump to one of the examples here. Then maybe you can use this examples. So let's see. This works out. Still taking time. Okay, so there you go. This is flood drought monitoring. So you can do this for various places, right? So you can pick your layers of interest. I might want to look at average precipitation. I can pick a layer that's average precipitation for a given particular time. You can take a look at the population density. So this is the population density map. You can get this even for India, right? Minimum temperature, right? So this is the minimum temperature file. But naturally, there will be some areas where you will not have the data. And that's largely because the models probably are not built in, right, for that. But essentially, you can do the same thing, across. And then, this way you can essentially, calculate various things. So if I go back and do the same thing for, see what else is interesting here. Change detection. Yeah. Let's see this. So I can actually even do, you can compare multiple layers and see, where is the change and so on. So this is Sentinel-1 data. It's band 8, Sentinel band 8 NIR. So you can pick, the difference. You can do a difference contours, right? You can draw contours, get that kind of information also. Right? So you can see the contours are not that big because there's, it's not a lot of difference. And this is the, you can calculate the difference. You can see these are the changes that have happened over time. So you can come up with this kind of estimates. So let us see. So that's the nitrogen in Aurangabad. It's ready. Let's take a look at it. And so you can see here that this is what the nitrogen looks like. Right. Load. So naturally, this is a one-time data. So you will not get a map, a graph, but you can actually download this data, right? So you can say here, you can perform actions, you can download the data, download the map, you can clone it, you can do any activity that you might be interested in to perform these things, right? So that is essentially on the data side, on how you can use the visualization aspect. Okay. So so as I said, there is a lot of tutorials available on YouTube. There is tutorials available on the GitHub, and feel free to connect with me. I'm happy to go through that. So let's take a look at a few more examples of how you can use this same approach for other functionalities, right? So if I go to the there are lots of sample applications that we have. So these are already there. So you can see you can get some estimates of climate change. You can do weather forecast. All these Python codes are available, by the way, and you can do crop IDing with the neural network. You can do deep learned wind forecast, drought conditions, global warming, nitrogen emissions. All of these tools are available, and a lot of the times for the functionalities you are interested in, it is as simple as actually taking the code and then tweaking it for your purpose, right? So let me just go through one or two examples that I feel maybe is of more relevance to you, and then that way we can get you guys also started, right? So let's start a look at the first thing called as the standardized precipitation index. So what is the standardized precipitation index? It's a drought index, right? And drought is a key component, right? And whether it is insurance or whether it is understanding the water deficit in the crops, we want to have an understanding of what the drought looks like in the future, right? And and so there are many drought indicators. Some of them are what we call as agronomic drought indicators, and some of them are actually just pure hydrological drought indicators, right? So the difference between the two, in agronomical or agricultural drought indicators, you actually take the consideration of the plant, right? You consider the plant, and then you'd see whether it is a drought situation or not. As an example, you might have really good rain, but if you're considering rice as an example, right? Maybe that rain is not enough for rice. Okay, so that's a drought condition for that. Whereas another, like in cold, in other kind of crops, essentially maybe that rain is enough. So so agriculture drought indicators are something that can consider the crop and then tell you whether it is a drought-like situation that you're experiencing and so on and so forth. Right? So that's the first one. The other one is what you call as the hydrological drought indicators, and hydrological drought indicators purely look at rainfall. Okay, and they look at rainfall historically, and then they say, compared to 20 years back, what is your precipitation today, right? And then come up with some estimates, right? So there are many such indicators. The standardized precipitation index is one of them. The standardized precipitation evapotranspiration index, SPEI, is another one of them. Similarly, there are more indices that are there that can be estimated. There's a Palmer index that can be used. So you can code all of these things very easily in IBM pairs and run it through Python. So let's take a good example at this. So the standardized precipitation index indicates areas of statistically significant excess or deficit of precipitation, right? So you basically calculate for each location the average precipitation, right, over historical data, and then you basically see, what is the current precipitation that you have right now, right? So you can have excess or you can have minimum, right? So the way it does it is it basically subtracts the mean precipitation for a given location over a previous period of time, and then divides by the standard deviation of the same historical data for that location, right? So if I have a map, I got to take each location, calculate the mean values, calculate the standard deviation, and then I got to estimate this difference between what is currently happening and what is the historical estimates. And based on the number of standard deviations, you can say whether it is excess or deficit, so on and so forth, right? So generally, you want to be within one standard deviation. I think that's reasonable. And you can say that you are having a normal season. But then if it goes beyond one standard deviation, that's when you have to have your thing. So if you have weather forecast data, for example, you can use this weather forecast data to actually see where am I experiencing drought-like conditions. And these are kind of maps that are today not there very easily, right? So a good example is the Karnataka State for Natural Disaster Monitoring Center. I think it provides excellent data, right? It's like really good data. I feel like there's a lot of opportunity for us to actually use that data to come up with nice drought indicator maps that are updated, to make it easy for for people to make decisions, right? So think of government trying to support the farmers. These kind of tools can become very, very interesting. Okay. So same with plantations, right? So if you are going to experience drought-like condition, and it is not the right stage of the plantation for that to happen, you can alert yourself and do the right steps to mitigate the problem. So these kind of indices can be calculated. So the way we do it is, again, the same. We just use the IBM, from IBM pairs import PAW, right? This is the server. You get the username credentials, right? And then you can essentially calculate the SPI with a simple user-defined function, right? So otherwise, this is going to be quite otherwise painful, right? So essentially, we this is the query. This generates the query. So you give the month, the year, the starting year of the historical data, the ending year of the historical data, and the spatial coverage, right? So what is the polygon that you are interested in? And you can draw your own polygon or use what's already there. So once you do that, essentially for all of the years, right? First thing we do here is we calculate all of the averages, right? Then once we have all the layers for all the years, we calculate the average. So here is the expression. So we'll say for year in range, year start to year end, we first calculate the average value, right? And then the second is average of the squared values. So that is for the standard deviation. And then we get the variance, right? And once we have the variance, essentially, you can query the SPI index, right? So if you follow this, I think line by line, segment by segment, you'll see how the calculation is essentially done. But essentially, we are doing three things. We are calculating the average value, we are calculating the variance, and then we are calculating the difference between the current value and the last this one. Okay, so that's what is happening here. Okay. So that's the year as an example I have given, and I submit the query. So once you submit the query, if the query is quick, it is going to give you the output right away. But if the query is not quick, right, it's going to take some time. You can say something called query.poll till finish. So what it's going to do is it submits the query with all your functions. If the output is immediate, within a certain amount of time, the server is able to calculate, it will actually give the output back. And we saw that in the previous use case, right? In this case, because it's a larger data, it's going to take some time. Okay, so we don't want Python to be stuck, right? We don't want it to be looking all the time. We don't want that continuous thing, because let's say you have a power outage or whatever, you have to start the whole thing again. Okay, so what we do in this case is Pairs automatically figures out, is it a smaller query or a bigger query? If it is a smaller query, it immediately gives the data. If it is a bigger query, it will return what we call as a reference ID. So you see this reference ID here. Okay, and so essentially you have this reference ID, right? Now what you can do is two things. You can either use the reference ID to query it maybe 2 days from now or 3 days from now and get the data. Another thing you can do is you can keep on doing something called poll till finished, right? So the first one, let us say, I did the query, right? And that's the one here. Let's say I do this query and it has given me an ID, right? So to keep on checking, right, until it is done, I can do something called as query.poll_ till finished. And when I do this, what it will do is it will take this ID. It knows that query has a certain ID, reference ID. It will check with the server every time. Are you done? No. Okay. It will wait for 10 seconds. Are you done? No. It will check again. So it will keep doing this continuously. At some point, it is going to be done, right? And that is when it will go to the next command, which is query.download. Okay. And then when you do that, it will download the data for you. And then you can say query.create layers, which will create your geospatial layers, right? So once you have all of these layers, right, you can then essentially, plot the various things, right? And if I do that, that's SPI. So in this case, I just queried for the mean value and I queried for the standard deviation. So once I have these two values, then I can essentially calculate, the precipitation index essentially, right? So, so if I take a look at this, that's what it looks like. That is the average value. That is the SPI for 2018. That is the current average. You can do variance. You can do other kind of calculations, right? Now take a look at this area. This is quite a big area, right? Now, if you were to do this all by yourself, essentially you have to download all of those years of data, you can do all of those calculations by yourself, and then come up with the estimate. But here, this is kind of simplified, right? Everything is done in the backend, and you essentially get the mean value map, the variance map, and from that you can calculate the SPI index. Okay, so I know it's a lot to quickly grasp, but feel free to go through this. Come back to me if there are any questions, and I'm more than happy to assist you on that side. Okay, so this is the standard precipitation index. That's something that I thought will be quite useful. Now, another thing that is of use to us agriculturists is things like vegetation indices, water deficit. You want to do maps like that, right? So so that you can actually calculate. So again, quick example. So this is I import all the liquid libraries. This is my I get the username. I put the various stuff here, and essentially I take a look at these different layers, right? So this is coming from Sentinel-2 data, right? And within Sentinel-2, the shortwave infrared one, okay? So shortwave infrared essentially is something that is very representative of water in the soil, right? So there are the Sentinel data essentially captures this this water deficit in two bands, SVR1 and SVR2. Okay, so the one is held in 49686 and 49687. This you can get from the from this area, right? So you can check which is the correct ID name. And once I have all of these layers, I can calculate the derived layers, right? I can say green minus SVR1, green, so this is basically NDWI, right? Normalized difference, water index, right? And then you have something called NDMI, okay? Average water. So then you can take the dates. So you can say I'm interested in 2019 7:30 and 2019 9 and 13. So 13th October, September, and 30th July. So I'm interested in these two times. So it's very easy to build the layers. You can say layers. I'm interested in all of the layers that are coming from raw layers. So here you see, I have created all of the raw layers here, right? So if you have multiple layers that you want to manipulate, this is the way you build. You first build the raw layers, the derived layers like this, like formulas, and then you basically query them. You can say LS format, and then you get all of these layers. Temporal interval is already here in the time key. So this is a little bit complicated example, but it'll I think it's a question of going through it, and you'll get the way it's done. And then once the layers are added, then say for LK in R layers and for DK in dates, you essentially say you calculate the various expressions. So for each date, right, you essentially calculate the various the indices and export them as output. So when you do this, right, and you submit the query, and then you poll till finished, and you create the layers. And once you do that, you'll get all your various keys. You can plot the same. So this is the modified normalized distance NDWI. So you can see the various estimates, and all this code is, by the way, available on pairs. So please take a look at it. And you can do the same thing with the normalized difference moisture index. Is just a simple formula again, but yeah, so you can do the same calculation. You can see the same thing here also, right? So you can calculate other indices, similar formulas, right? And do the same thing, right? So this is one example of normalized, how do you use the water deficit calculations? And this is something I feel that you can apply for your work right away, right? Now, there are many ways to do this problem. One is, this is the most, I would say, computer engineering wise, the best way to write it, but then you can also simplify it with the simple user-defined function, right? So, so I would say suggest that try both ways and see what fits you. Right. So that's yeah. Go ahead, Karan.
So, do you have any queries, participants?
Good afternoon, sir. Rajshri here.
Yes, madam, please.
Sir, actually, the things that sir has shown just now, we have used the data set and we have fired the queries or used the user-defined functions there. My question is, normally when we use the data set, the very first step that we apply is pre-processing. So is it like the data set that that are provided through IBM pair, they are already cleaned?
Yes. So there are, so the way we look at it is, there are some data sets that are very commonly used, right? And then some data sets that are very rarely used, right? So most commonly used data sets are processed and cleaned, right? And they're available for you for your application, right? So so that's an advantage of using the same.
Okay, sir. And sir, if explicitly I have to write any pre-processing code, whether I can do it in this platform?
So see, the user-defined functions are simple ways of manipulating the data that is already there, right? But if, let us say you want to do some extensive pre-processing, that is a little complicated right now in pairs. So you have to then download them and then do it all by yourself, right? But having said that, there are other things that we are building right now at IBM Pairs, where you can actually write this pre-processing steps, the complicated ones you want to do, right? And then get it done the server side itself, rather than downloading it, right? That's coming later.
Thank you, sir.
Yeah. So so that's on that side. Now there are other few more examples that are out there, right? So I don't want to confuse a lot of you here. So my suggestion is maybe yeah. So I think I recommend that please feel free to take a look at all of these examples that are there on the GitHub of IBM Pairs. I'll share the link with all of you. Feel free to go through them, and then come back to me, if you feel like there are any questions are of interest, right? So so I think Dr. Ganesh, that's what I had for today. I hope it was useful.
Yeah. Yeah, sir, can you show some data on how IBM collaborating with the Institute, Education Institute and research purpose? Any other collaboration you are using, sir? What kind of collaboration as a education institute we can tie up with IBM research? Any
scope, research area, something, sir?
Yeah. So the way IBM collaborates with academic is we generally start a relationship through intern programs, right? So so we believe that the best way to build a relationship is through students, right? Because that's the right way to go, right? So we start with an internship program, and then from there on we build various things. Now there is also things we do, for the government's purpose. So we work with institutes to look at a very specific problem and see how we can solve that problem. And so that's another way also we can collaborate, right? So I can share more content on the internship program with Ganesh and the team.
Thank you, sir. So if you have any other question, please discuss with our resource person. Any other clarification?
So, dear participant, do you have any queries? Please discuss with our resource person. Just raise a queries.
And as I said, feel free. This is I'm a strong believer in collaboration, strong believer in supporting fellow professionals.
Sir,
So,
one question in chart box from SHRS: how to choose agriculture data with their parameters, and how to payroll or build model.
Okay, so agriculture data, see, there is nothing like agriculture data. It's mostly weather data, right? Soil data, things like that, right? Now, I would say always start with, in agriculture at least, always start with the data sets that have been used before, right? So if you think about satellite data, what is the first satellite data that comes to your mind, right? Sentinel. Everybody uses Sentinel-2 data, right? So there's no need to guess beyond that. Use Sentinel-2 data, Sentinel-1 data, right? MODIS data, right? And another opportunity, for that I feel is all of this data that ISRO has, right? I feel like academics, like all of you, we have an opportunity to come together and actually work with organizations like ISRO to bring those kind of data sets into play. But because the data sets are not available, I will say that start with ones that are already used. So if it is soil data, focus on things like soil grids, right? So, and how would you know in any given area what is the right one, right? That's a good question. And the question and the way to do it is just go through literature. There's enough literature out there today, right? You put in your problem, you see what is the most common data set that is being used, and use that, right? So that's one thing. And how to build a model for prediction. I know that's a very important question. My goal is, there is this idea of something called Occam's razor, right? And the idea is simple. If you have multiple solutions to a problem, the solution that is probably the right solution is the one that is the simplest, right? So my suggestion when you're building a model, right, is let us not overcomplicate, right? Find the simplest solution. So as an example, I think Dr. Abhishek was mentioning that sometime back. That is, disease models, right? Yes, I can go ahead, build amazing, physical-based models where you consider the biotic aspects of various things and do all these things. But we know for a fact that, simple weather-based, expression-based, mathematical expression-based models work just fine, right? Maybe they are 10% less effective, but they do the job. So the thing is, why should we burden ourselves with computation when we don't have to? So the first thing in agriculture for me is always pick the simplest model, and the simplest models for most of the problems are already there. So once you have those things, then look for something like an easy platform like IBM Pairs, to build those models, and the code is already there. And it takes basically, for a newcomer, it takes maybe 1 or 2 weeks to kind of get through the grind. But I think once you are there, you should be able to solve all by yourself. Yeah, I hope that helps. I think it's SHRS. I don't know the full name. Apologies. And where to develop forecast models is Dr. Abhishek is asking. And I would say, use Python, right? Yeah, so I would say use Python, Dr. Abhishek, right? So I think we have to align ourselves to the industry standards, right? And today, the industry standard is Python. So I would suggest, use Python. And if you want me to suggest a few courses for Python. There is one really good course in a place called Udemy. I think it is called Udemy. So I think for people who are interested, let me quickly check what's the name of that course. A lot of people like it. Udemy, course. I think 1 second.
Asking for how our language is something.
So this one, yeah. Can you all see this link? Yeah. So this is a really good course, right? I mean, it's very detailed for somebody who wants to get started in Python. I mean, there is no better course than this one. So let me just share the link before I forget. Okay. Yeah, I think it's very reasonably priced and it should really get you started. Yeah. Hope that helps. Let me share it with all. Everyone, just share. Yeah. So that's a one good course. And what's that question about R, Mr. SHRS? Yeah, R language, right? So yeah, see, I was a R addict, I would say 15 years back. Okay. Everything I should do in R. Okay. But the fact of the matter is, R is, so there are two things I want your kind attention to. One is, yes, R is equally powerful like Python, right? But because everybody is doing things in Python, all the libraries and the nice things that you can use along with these programs, the packages or all these things, you will find more and more such packages in Python, and you will not find them as much in R. Okay, so it puts you in a disadvantage if you focus on R, number one. The second thing is the code from R is not easily scalable, right? So for example, if you write a code and for some reason, let us say the government or somebody wants to plug it in to their solution, it is not very easy. Okay, it doesn't scale well. Okay. Whereas Python scales beautifully, right? I mean, you can take the Python code, convert it to an API, and expose it to your even mobile application solutions and all of that, right? So any day, Python is a much stronger solution for various reasons, right? It also consumes less memory, right? You can run it on clusters. You can run it on cloud. You can do so many other things. When you start dealing with big data sets, it becomes a lot easier. So that's the only reason why I suggest Python over R. Yeah. Farhana asks me, sir, can we machine learning application business? If so, what are those ML algorithms, right? So I'm assuming that the question is machine learning applications, right? So yeah. So machine learning algorithms, there is no one specific machine learning algorithm, right? I think, Farhana, the most important thing to understand about machine learning, especially in the agriculture context, is you have to have a strong foundation on the statistics, right? I think if you understand statistics very well, machine learning algorithms or even AI, they're all quite simple, okay? So I would say, Farhana, that a good place to start is to understand machine learning algorithms. And the link I just shared with you on Udemy, it actually provides a very detailed explanation of these various concepts. So I would say start with something like that, see how you feel about it, run through the code, and then you'll feel good about it. Okay. Do we need abiotic data along with data from IP intelligence? Okay. So abiotic data. So all of the abiotic data is already on IBM pairs, right? So you can use the state that data. So as far as biotic data is concerned, that data intends to be not available as much. So for that purpose, you have to use the biotic data separately. Yeah, it's not generally something you get as a map, right? So think of IBM pairs as something where if you have some data as a map, there's very good chance you'll find it on IBM pairs. Okay. SHRS says any NLT is available for all Indian languages. NLP is what I think you are referring to, SHRS. I think NLP is applicable. Right now, it is applicable to Hindi, and I would say some of the more common languages, but it's not very advanced, right? And I think NLP for Indian languages is still something that is evolving, right? So some of the companies where a lot of the good work is happening there is in Reliance, right? So Reliance has this place called the Geo Center for AI Center for Excellence. Okay, so so there a lot of work is happening at a fundamental level on how you can create better NLP for Indian languages, right? So I would say wait for it, but that's what it is. Okay, Rajeshri Shegde says, how is IBM pairs different from IBM Watson? Okay, IBM Watson is a AI intelligence tool. Okay, it provides you various AI platforms, right? For example, neural networks, deep AI, reinforcement learning, simple machine learning algorithms. It provides those kind of things, right? So in many ways, it's like the Azure Machine Learning Studio, okay, or the Amazon SageMaker. IBM pairs is very unique. You don't see that kind of thing in Azure or in Amazon. It's all about geodata, geospatial data, right? How do you manage geospatial data? That's what IBM pairs is about. So if you're talking about geospatial data, it is IBM pairs, right? It's a data repository, right? So you can take the data from IBM pairs and build something on Watson, for example. But then you can do the same thing in Amazon also, right? So you can take the same data, build a model in Amazon, in Watson, on even your computer. That's up to you, right? IBM pairs is just a data repository. How do you optimize geospatial data, which tend to be very heavy? That's the goal. Yeah. Does it answer your question, Rajesh? Cool.
Yes.
Any other questions, guys? I will just also share with you my email. That's my email, and you can find me in LinkedIn with this name. Yeah. So feel free to connect, and I can definitely assist you. I think I just only shared it with Dr. Abhishek. Everyone. Okay. Sorry. Okay. Okay.
So I have a query. So I have worked for the geospatial data on LOS and ArcGIS softwares. And also on Tableau and Power BI, we can do geospatial data analysis. And as you talked in this workshop for the IBM pair. So according to you, what would be the most advanced and most sophisticated tool for the geospatial data analysis?
By a long shot, IBM pairs, not because I work there, right? It's a pure unbiased answer for multiple reasons, right? I mean, you have all the data sets that are there. Now think about Tableau, right? You can do some basic visualization and things like that, right? But you can't do analysis, right? There are lots of tools for geospatial visualization, lots of tools, but there is not a lot of tools for pre-processing the data, extracting the data, things like that, right? So IBM pairs strength is there, right? So if you are looking for visualization, right, only pure visualization, then IBM pairs basically provides all the data. You don't have to download anything. You can just see it for, on the website and see what makes sense, what doesn't. That's simple, right? But if you're looking for analysis, if you're looking for analyzing over large areas, large time spans, then there is no comparison between what IBM pairs offers and Tableau and other things. Yeah.
Okay, thank you, sir.
Yeah, you're welcome. Dr. Jayashree says, are you collaborating with the Education Institute and impart analytic course? Right now, we are not. We are doing some internships at IBM. We are supporting that kind of things. But I think if there is a interest on the agriculture side, let's say the consortium of institutions like we are seeing here today, where they would want to do that, then definitely we can, that's a discussion for like later. How to apply for internships? That's a great question. I will share those links with Dr. Ganesh and Dr. Venugopal, and they can basically, then forward you to all the attendees. Great.
So I would like to request a participant, please, do you have any queries, please ask to our resource person. So feedback form also shared at the chat box. So Ganesh sir.
Yes, sir.
Shall we wind up, sir?
Yes.
Almost. Yes. So thank you very much, sir. Dr. Naveen T from IBM Research, Bengaluru. Really, session is very informative, sir. So how you started, how just explained the concept in a practical way. It's really